like, I'll give you a velocity function. I'll say velocity of t is 8 minus t cosine of, I don't know, 1.5 to the power of t. Something like that. And let me graph it because I actually don't know what that looks like. Make sure it's actually something. Yeah, let's go from like 0 to 1. It's not enough. Let's go 2. Is 2 enough? Let's go 0 to 3. Doesn't come back. 0 to 4. There it is. Okay, let's go 0 to 4. 0 less than t less than 4. All right. So would you be comfortable graphing something like this and figuring out where it crosses the x-axis, things like that?
Yeah, I do know how to graph on a calculator. That part wouldn't be that hard.
Okay, I asked because that's key here, like getting the right window and getting the right like viewing angle and all that stuff could really help, because there's a couple of key points that we need here. So I'm gonna graph it with a much nicer tool, and I'm gonna snip that in so we can talk about it. All right, here we go. So this graph here looks something like this. Okay, and you can see it crosses the t-axis at a couple of different places. All right. So the first thing I could tell you is that s of t is equal to s of 0 plus the integral from 0 to x v of t dt. Have you seen that before? We've probably looked at that together.
I think so, yeah.
Yeah. So to answer this question, let's just say I told you somewhere that the initial position is 2, okay, and then I want s of 3. So s of 3 would be the integral. It would be s of 0 plus the integral from 0 to 3, and then this v of t function dt. So in short, it's 2 plus, and then you want to use that math 9, that fn int, for this function here. So will you give that a try, please? And I'll do it as well, and we'll see what we come up with.
I got -2.02, etc., etc.
Yes, we'll just say to 2 decimal places. So that's great. So that means that, and just to be clear, that there's more area, like if we look at where 3 is, there's more area below the curve than above the curve, and including that starting position as well.
Mhm.
Okay. So I could ask you any number of questions. I could ask you, S of 1, S of 2, really anything in there. But then you get to the more interesting questions, the one that you're more likely to see on your exam. So we'll call that B. The first thing I could ask you is the total distance, and the total distance traveled by the particle. Total distance traveled is S of 0 plus the integral from 0 to 4 v of t dt. And we could get some number just like we did in the last problem, but that's pretty straightforward. The more challenging one here is the total displacement. There's really 2 approaches here. The correct one is to find the integral in each of these regions, A, B, and then C.
Mhm.
The cheat, or the shortcut, is to graph is to use the absolute value of this function. Have you seen that before?
I have not seen that before.
Okay, so the shortcut here would be S of 0 plus integral 0 to 4 absolute value of v of t dt. So why don't you try that? And I'm going to write out the longhand form, and you'll see that we get the same answer when we're all done here, roughly, because I've got to use those points. All right, so I finished up my calculations here. I'll add mine up, and they should equal what you found here. 2 plus 2.53. Notice I have to subtract the area that's underneath the axis, because it ends up being positive, because you want the total displacement. And so this all ends up being 13.53. Did you roughly get that?
I got exactly that.
Perfect. Okay. So a couple comments here, like go out far enough on your limits. 3 decimal places, 4 decimal places is probably good. Depending on the problem, make sure you keep track of your signs and so on. So that's the total displacement. That's taking, the areas that are positive, making them positive, negatives become positive, positive stay positive there. Okay. So the next question that they could ask would be something like where is position a min or a max? Okay, so there, to answer this, there is a kind of a recipe here. Like you want to start by figuring out what happens at 0, and then we know that one, that's 2, and then the next point that you care about is where it crosses. So it's at that 1.14, something like that, and that is 2 plus 2.53. So 4.53. Then you care about, well, what happens at the next one, which I guess, what was it, 3.823? And this time you're actually going back to part A. You're going back to where you don't care about displacement. You just do the integral from 0 to 3.283. So now you actually do subtract. You subtract that, what did I say there, 8.88. And you don't subtract a negative, like it literally is 8.88. Okay.
Mhm.
And we get a number there. We should get that number here. So, and I'm only guessing. I mean, I wish I knew for sure that this was the type of problem you'd see, but this is kind of the next logical thing. So that's minus 4.35. And then the last one is at 4. It's 2 plus 2.53 minus 8.88 plus, I don't know what that last number I got was, 0.12. Okay, so that's minus 4.23. So you look at this list and you ask yourself, which one's the biggest? So that's the max. And which one's the smallest? And that's the min. And that's how you make that declaration.
Okay,
And you have to do it at each of those. You have to do it at the endpoints, and then at any of those breakpoints.
that makes sense.
Okay. So I mean, I guess there's a few other questions we could ask here. Like, I could ask you about the acceleration as a function of time. How would you do that from this function right here?
Isn't acceleration the derivative of velocity?
Yes. And you know, you might think, well, why is he even asking me that? Well, because you've been doing so much integration, sometimes students don't remember, like, yeah, we did that. So would you kindly find the derivative of this for me?
Okay.
As a reminder, it is product rule. All right, so I'm just writing down the derivative here. Yours may be in the other order, but there's a lot of chain rule in the one part where you got to take derivative of cosine and then derivative of this and so on. So be aware that you could be asked to do that. They could ask you for the acceleration at a point, or they could, or not, and so on. Are there any questions about sort of this velocity position stuff that you feel like we didn't cover that could be on a test or quiz?
No, I think that pretty much covers it.
Okay. Is it okay if we move to some work problems? You said some work integral problems.
Yep.
All right, so let me pull up a possible work problem. Just a moment here to find it. All right, so here is kind of a classic example problem. Let me snip this in. All right, so work. We have a cable that weighs 2 pounds per foot attached to a bucket filled with coal that weighs 800 pounds. The bucket is initially at the bottom of a mine shaft. And then there's some questions I give here, but the scenario is you got a rope attached to a bucket down here. The bucket weighs 800 pounds, but the rope also has weight. So when you start, actually, let me move this over here. When you start, you're pulling both the bucket plus the rope, which, I mean, doesn't sound, I mean, that's like, of course, but the rope has, meaning like it's 800 plus however much rope you have times 2 pounds per foot.
Mhm.
And when you get to the top, or when the bucket gets to the top, you're still holding onto the bucket, but the rope goes to zero, not because the mass of the rope, I'm sorry, not because of the, they call this, what is it, like density, anyway, can't think of the name, but it's because the length of the rope is now 0 times 2.
Mhm.
Okay, and you still have that 800. So what you need is some sort of an equation that expresses like this right here, some sort of equation that obviously changes from where you start to the bottom. So an assumption on these problems that I think is a little bit uncomfortable is they consider this to be x equals 0, and what they mean is 0 pulled rope.
Mhm.
So since no rope has been pulled, that and then x equals at the top 500, that means that there's 500 feet of pulled rope.
Mhm.
So you have to come up with a force function basically, and the force function, it's a straight line, it's linear. It's 500 times 2 at the bottom when x is 0, and then it's 0 times 2 when you're at the top. So if you think about this real hard, or write the equation line, you end up getting 500 minus x times the rope density. That's what I was looking for, the rope density. Okay, and then you always have this 800 because the bucket is always full.
Mhm.
Okay, so if you write this out and then you combine like terms, you get 1000 minus 2x. So you have 1800 minus 2x. And then work is the integral from, and it's starting point to ending point. So we'll just write it there, start to stop, and it's your function dx.
Okay.
And anything about this unclear? Anything like is that all okay?
That's all okay.
All right. So the in this problem, like part A could be, what is the work to pull halfway? So it's a 500, 500 feet deep, but you're not going the whole way. You're going from 0 to 250. So those are the limits of your integral. Work equals the integral 0 to 250. And then I got to go find, I think it was 1800 minus 2x dx.
Mhm.
Okay, and you can do that in a calculator, you can do that by hand. And then the work to pull the second half. Okay, so like once you have the force function, it's just putting limits of integration in.
Yep.
Okay, so probably nothing about that is all that difficult, but there are some like variations in the way, like you could set this up, like you could set it up where x equals 0 is at the top and x equals 500 as at the bottom. What could change is your force function, your limits, things like that, but you kind of get to pick how you want to do this type of problem.
Okay.
All right. So let me give you another work example problem. All right, a 20-foot cable weighs 80 pounds and hangs from the ceiling of a building without touching the floor. So there's a ceiling. It's a little weird, but okay, fine. You got a rope, and the whole length of the rope is 20, but it also has a mass of 80. Okay, and this rope density that you really care about. Maybe that's not the right word, but it's pounds per foot. So you literally take this 80 and you divide it by 20, and that gets you the 4 pounds per foot.
Mhm.
Okay, and at the top, here, like, well, if let's see, what does it ask for? To lift the bottom end of the chain. Yeah, okay. So they want the work. Sorry, you're starting here at the bottom. So this is, I mean, it's kind of odd. Like somehow this chain is going to go, or rope is going to go up. And when you're starting at the bottom, you have to lift the whole amount of this. So like when you start, it's 80, it's 80 pounds. But at the top, it's 0 pounds.
Mhm.
Okay. There's kind of the only thing that's kind of unclear is that to me, I guess I need to read this question a little bit more. Is like, do they actually lift the whole thing up, or does it kind of loop? Like if you were to pull something up, they'd only go halfway. Do you see what I'm saying about that?
Yeah.
Okay. So I'm just looking at this problem from another university, and they do say like, oh, it does only go halfway. But let's just make it our own problem. Let's say you're going to lift this thing all the way up, okay?
Okay.
Because that it makes it more like the last one that we did. So it's starting 80 pounds, but at the top it is 0 pounds, okay? So how do we do that? Well, it's the distance. It's this 20 minus x times the 4 again, okay? But this time there's nothing like attached to it. It's not like, someone hanging out at the bottom. It's just this. It's just the rope, okay? And what you do is you test, like put in x equals 0 and see if it gives you 80, and plug in x equals 20, and see if it gives you 0. And this one does. Is that okay?
Yep.
All right. So the work now is the integral from the start to the stop. And in this case, it's the 20 minus x times 4. Now you could distribute in 80 minus 4x and go on that. Okay, but these are kind of your work scenarios. Now, the only other one that you might see is a spring problem. Is that something you have seen or want to see, or should we move on to something else?
I'd like to go over that real quick.
Okay, that is actually example 1, but let me modify it here because it's kind of unrealistic. So it says a 100 Newton force is required to stretch a spring from 2 meters to 4 meters. Okay, and we assume its natural length, and that means it's unstretched length. Have you taken physics? I'm sorry if I've asked you before.
I took physics 1.
Okay, so this is part of mechanics, but its unstretched length is 2 meters. Okay. All right. So the first equation you care about is F equals KX, Hooke's law. Maybe you saw as F equals minus KX. They don't do that in calculus. F equals KX. So they tell you force. They tell you 100 equals K. The F has to be in newtons, and the X has to be in meters. If it's in like centimeters, you got to convert. And that was the problem I was about to give you, but the unit conversion isn't really part of this. So they give you the stretch length. It's not 2, it's 4 minus 2, because that's how much you stretched it. So 100 equals 2K, K equals 50 newtons per meter. You put that back in. Notice that's direct variation.
Mhm.
Probably did that a bunch at some point. So your force function is 50x. Okay. So part A could be, what is the work to stretch from 3 to 5 meters? So this is the integral from, okay, 50x, because that's your f of x function, dx. Now you got to be careful because your unstretched length, your sort of your starting point is 2 meters. So the bottom bound is actually 3 minus 2 to 5 minus 2, because it's really 1 to 3.
Okay.
50x dx. Okay, so a part B could be, actually, let's get a number here because I want to give you a part B that's somewhat reasonable in case you want to look at this again. 50x from 1 to 3. Work is in joules. This is 200 joules. Okay, so let's say a person has 300 joules of work available. Okay, how far can they stretch the spring?
Mhm.
So this is the 50x, and we're doing it from 2 to an unknown position. Now it's 2 because that's its unstretched length.
Yeah.
Okay, so I'll put x up here, dx. So this time and this equals 300. So this time it's a working backwards problem. We have to find our antiderivative, 25x squared, evaluate it from 2 to x equals 300, and we solve for x. So it'd be 25x squared minus 25 times 2 squared equals 300. So so we divide x squared equals x equals plus or minus 4. So it actually indicates that you could stretch it in one direction or the other, but because we assume positive, we'll say 4.
Mhm.
Now also keep in mind that I could have talked about compressing the spring in any of these problems, and that's totally reasonable because you can stretch it and compress it. Its unstretched length though would probably be a little bit longer than the 2.
Yeah.
But this isn't a physics class, so we don't have to worry about that in some regard. So, all right. So we've done kind of a calculator, velocity, investigate position. We've done a without calculator, a couple of work problems. Where should we go from here? What's kind of your next weakest thing? Or
I would say volume in general.
okay, you want to do x-axis, y-axis, both?
From what I've heard, there's more on x-axis.
Okay. All right. So, all right. So let's say I'd give you y equals e to the x. Let me actually graph this so that we can and y equals x squared. See if this does anything. Yeah, that's okay. And let's say we want the area between from, actually let me change this up a little bit here. So I'll make this better in a moment, but ooh, actually that's not going to be easier. I'm sorry, I'm trying to make this more complicated than I need to. So let me just go back to this. Could you set up the area from 1 to 2, x equals 1 to 2 on this one, and get the correct top minus bottom here?
Okay.
And if you're not sure, let me know. I can provide some hints. So hopefully get something like this, e to the x minus x squared, and then find your antiderivative. So it's e to the 1 minus, I'm sorry, e squared 1/3 2 cubed minus e to the 1 minus 1/3 1 cubed. So e squared minus 8/3 minus e minus or plus 1/3 So you might get something like e squared minus e minus 7/3, something like that. Okay, now I know you said you want to do volume, but this was just kind of a starting point for this. So we'll do volumes next.
Okay.
Any questions on that? How to do it? right.
So to figure out which one comes first, which one comes second,
Yeah, the best. Go ahead. Sorry.
you want to point in between them, right? Like in between the
Exactly.
bounds, right?
Yeah, and I didn't pick a good one. So like it would be kind of more of those, like one of those where you actually need to like try it at 0, even though that's not in there. E to the 0 is 1, x squared is 1. So e and x squared never catches up to it.
Mhm.
Because you and maybe you would know like e of 1 is 2.7 and 1 squared is 1. Like it's not great, but like there is some expectation that you know this there, and this wouldn't be one you could solve because it without a calculator. So you would be kind of, but the other thing is you could check your answer and be like, well, is it positive or not? But you might not know. I mean, you may not know what e squared is.
Mhm.
So a little bit of guessing there on that. Okay, let's try another one here. Let's go with y equals 2 square root of x and y equals 1 over, nope. Let's see, x. Yeah, here's a classic kind of. So we want the volume between, or the volume by revolving, revolving the area between y equals 2 square root of x and y equals x. And we're going around the x axis. So this time, you don't even know where they intersect. Like before I said, oh, just, here's the window. You should reasonably expect to set these equal to each other. Okay.
Mhm.
Any idea how to solve this without a calculator?
I could probably figure it out, but it might take a second.
Sure. So the square both sides, that gives you 4x equals x squared. Move this over. Factor out an x. And you get x equals 0, x equals 4. And that might be consistent with what you kind of see the graph looking like y equals x looks like that, and 2 square root of x looks like that. You can actually see they intersect up here.
Mhm.
So if they don't give you the points, you got to find the points. If you have a calculator, graph it, find the intersection. If you're more comfortable by hand, do it by hand. Use some technique you've learned in the past. So do you see that this is a washer problem?
Yeah.
This is a washer problem. And your big R is the top function. So your top function is 2 square root of x. So your volume here is integral 0 to 4, because those are the x bounds, pi. Your big R is 2 square root of x squared minus x squared dx. So this becomes 4x minus x squared, and then we got to find antiderivatives. Okay. Any questions on how you might do this, or is this kind of clear?
That's good.
It's good. All right. Let me give you one to do here. Let's go. All right, so here we go. Let's say I want you to revolve the area between y equals x squared minus 4, and then y equals minus 2x squared plus 8. And we're going around the x-axis.
Mhm.
So see if you can set that up. Actually, I just grabbed this. I'm sorry. This one is not a revolve problem. You would actually just find the area between these. So did you happen to find the intersection yet of these?
I got positive and negative too.
Yeah. So x equals plus or minus 2. So this is just a top minus bottom problem. Okay. And then to do the volume, we'll do something different. We'll do cross sections or something. But if you don't mind, can you give me that volume? I'm sorry, area between calculation?
Yep.
How are you doing on this one?
Um, I made a minor area where I forgot the negative in front of the negative 2x squared, but I should be done with that in 2 seconds.
No problem. Yeah, signs just throw everything off here.
Doesn't it negative 2x squared minus x squared combine to negative 3x squared?
It does, and I was wondering why this answer is different than what I calculated using the calculator.
That's the exact same thing I get, so.
Yeah, it's I actually always get the answer. Like if I had a calculator and I were a student, I would do the calculator first and then make sure my work matched that, because it's very easy to make a mistake. Still not getting the right answer. Oh, the correct answer is 32. And I don't know why I don't know why I don't have that here, but
Negative 2 cubed times negative 1
yeah.
is
Oh, I
positive
see.
8.
There you go. There it is. Thank you. All right. So I found a y-axis problem for us to close out on. Probably take the rest of the time, unless you want to do something else, but I think this is a reasonable one to ask you to do. So let me, these are hard to come up with on my own. I mean, they have to like work out nicely and have nice intersections and, you know, be possible. So here they want you to go, it says they kind of modify it, but we'll just go y-axis. So first thing I would do is set them equal to each other. And again, you would square both sides. So you get 4x minus 4 equals x squared minus 2x plus 1. Get everything on one side. You get x squared minus 6x plus 5, x minus 5, x minus 1. So x could be 1 or x could be 5. And then you throw it back in like to this one here. When x is 1, y is 0. And when x is 5, 5 minus 1 is 4. And you need those points. I'm sorry, you need the y values to go around the y-axis. So it's going to be integral from 0 to 4. And then the part I think is hardest is like, well, which is right, which is left. So you actually need to solve both of these for x. So this is y over 2, then you square it, equals root x minus 1 squared. So you get y squared over 4 equals x minus 1. X equals y squared over 4 plus 1. And this other one's a little better. It's x equals y plus 1. So to figure out which one is right and which is left, you pick a number for y between 0 and 4, like 2. And this gives you 3. This one is 2 squared plus 4. I'm sorry, 2 squared over 4, which is 1, plus 1 is 2. So you can see that this one is actually more right than the other value. Okay. If you get the same number, you know, it means you made a sign error. So but what may not be clear, and that's where you might have to graph these, is that it actually has kind of this shape to it. So it's a, if you wanted the area, it's just right minus left. But if you wanted a volume, you gotta get your big R, and then you gotta get your little r there. So this is a washer problem. This is a pi, and then y plus 1 squared minus quantity y squared over 4 plus 1 squared dy. And like I said, if I were a student and they like say, hey, calculators are fine, you still got to show your work, I would absolutely get an answer like for that, and then make sure my work matched, because if you do it the other way, you don't know whether it's right or wrong for that.
Okay.
So your x direction is always top minus bottom. Your y direction is a right minus left. So So out of the rest of the list here, things like we didn't cover, cross sections are really no different than volumes. You just find a different area function. We didn't do any net change problems, but net change is typically how much going in minus how much going out. We
Mhm.
didn't do any arc length problems, but arc length is a formula, so just keep that in mind. You can just look that up for that. So that does take us to the end of our lesson for today. I will send you the notes here shortly. And thanks so much for scheduling. I'll see you next time, and good luck on your exam.
Thank you.
You're welcome. Have a great night. Bye now.
You too.